Welcome to week 11 lectures of applied multivariate statistical modeling. Very good morning. In this week we will discuss factor analysis, basics and orthogonal factor model will be discussed now. We will also discuss assumptions. Let us see the next.
Today our discussion will be on factor analysis. Factor analysis. So I will start with the famous quote of Lord Kelvin, the British scientist. What he said, when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. The measurement is necessary. That means, what I mean to say, suppose whenever you talk about any system of its behavior, then the behavior pattern you must be able to measure. You must able to give a number to it. For example, in our department, there is one important area to work on, that is supply chain management. And we talk much about supply chain coordination. So we may say that X supply chain is coordination good, Y supply chain coordination bad, like this. When you talk of in this manner, that this knowledge is not perfect. If I say that yes, suppose there is the particular food, let it be paddy supply chain in Indian context, then you are able to tell that okay, at the local level, block level, or at the state level, that the different agent how they are coordinated and the measure is 0.9, suppose something like this, then this is a valuable knowledge. That is what is important, and that is said by Lord Kelvin. So, second gentleman, I think he is one of the famous statistician, Charles Edward Spearman. So, Charles Spearman, he measured the human intelligence. That means, what I mean to say, suppose person X intelligence level or IQ is some value, person Y some value like this. So, human intelligence, you can understand it's a such a concept. It is not that 5 kg of rice or 25 kg of some other product. It is not like this. You cannot just take some this type of measurement and go. It is a soft thing. For example, like supply chain coordination is also a soft thing. Your mental measurement of that intelligence, human intelligence, it is not visible. These all are basically unobservable things, unobservable. I can say the coordination is unobservable. You cannot directly go and measure. Intelligence also unobservable. Then question comes, how do you measure such unobservables? So, there are certain techniques, and the factor analysis is one of such techniques, and probably the one of the best technique that is used in measuring unobservables. Okay. The key concept here is measurement is required, but measurement is not easy. The world is abundant with immeasurable things which cannot be measured. I will give you some example here. A psychologist is interested to measure the mental ability of a person. A safety manager is interested to measure safety environment of his workplace. A supply chain analyst is interested to measure supply chain coordination. A marketing manager is interested to measure the purchase intention of customers. A welfare officer is interested to measure the quality of work life in factories, and many more. You can find out 100 such items, examples, where you see that it is not there is one instrument, hardware based instrument, you will go and measure. It is not possible. However, 90% of the cases we take decision based on this type of concepts. So, another word is, I want to say that concepts. Many a time we say that constructs. So, by saying this, we are basically unobservable concept, construct. By saying this, we are basically telling to you that there are certain things which are hidden, unobservables, that is not directly measurable, but those things are very, very important, and because those things causes some things to happen. For example, if there is not proper coordination in the supply chain performance will be poor. Okay. Suppose the quality of work life is not good, then the human productivity, safety and all other issues in the company, that will be poor. So, that means although there are many things like this which are unobservable, which are concepts, which construct, hidden, these cannot be directly measured, but their effects means because of the presence of these constructs or concept or unobservable things manifested into different symptoms. What I mean to say? I mean to say that suppose there is construct, concept, or we can say factor. So, these things manifested in terms of symptoms. So, because for example, someone is risk taking in nature, So, what will be his symptoms? He will maybe a rule breaker, not follow the traffic rule. So, you are able to see this symptom, that not following the rules may be rebellious, but it may be show that risk taking, that attitude, what is in his personality, that is the main reason, the cause of this rule breaking. That is why we say that something had hidden or immeasurable constructs or factors are there which are causing these symptoms, and these symptoms can be used to measure this factor or construct. Okay. That means factor or construct causing the symptoms can be used to measure construct. Getting me? So, essentially the concept is like this. If I say this factor is F and there are several symptoms which we can say the manifestation or manifest variable, the symptoms are nothing but manifestation of this hidden thing. So, this manifest variable, if we say x, correct. So, that means what is available with you? You are observing this x and you want to quantify f. Getting me? You observing this, and so that means with this, if we can say something like this, that you are observing x which is p cross 1. That means p number of, this is a variable vector having p manifest variables, p manifest variables. Okay. It definitely coming from a population. Now, suppose this x is having the mean vector like this, which will also be mu 1, mu 2, mu p. This will be p cross 1 vector. This x is also having a covariance matrix which is sigma, capital sigma. This one is, you can write sigma 1 1, sigma 1 2, sigma 1 p, sigma 1 2, sigma 2 2, sigma 2 p, like this, sigma 1 p, sigma 2 p, sigma p p. Okay. So, this is what is known about the population. That means there are p variables, p mean vector, p cross p covariance matrix. The mean, that mu 1 to mu p or sigma 1 and to sigma p, these values may not be known, usually not known from the population point of view. Okay. Now, what we have described here, we said that in this place we described that these x you are observing because there is certain underlying causes or hidden constructs or factors. So, if this is the case, if we consider now, consider m factors. Okay. So, then my f is the vector of factors which is m cross 1, this will be your f 1, f 2 like f m. And you were saying that whatever you observe in x, this is because of the causal factor f, f is causing this. Then we can write linear regression like equations also, but first I will pictorially represent this. So, what we can write, I have x 1, this is my one observed variables, my second observed variable is x 2, like this my last observed variable is x p, and we are saying that there is factor f 1, f 2 and f m, m factors, which are causing these x variables to occur, to happen. So, in this case I can say x 1 is caused by f 1, x 1 also caused by f 2, like this f m. What we are trying to say, that there are m factors which influencing this x 1. Because of these factors x 1 you are able to observe. So then if I write like this, f x1 is caused by f1, I can write lambda 1 1 for x1 1 f1 1, then lambda 1 is caused by 2, lambda 1 is caused by m. Okay. So what you can do, the same thing will happen to x2. So what we will write then, this one will be lambda 2 1, then lambda 2 2, lambda 2 m. Then another last one is your correct. So lambda p 1, lambda p 2, lambda p m. When we are assuming, what we are assuming, this f causing x. So these are the all influencing coefficient, influential coefficient. So factor f1's influence on x1 can be measured through lambda 1 1 like this. Now in addition to this, what we assume that these factors collectively cannot explain everything about x1. So there will be one error term. Correct. Now using this, but please remember here we are not talking anything about the relationship between f1, f2 and fm. When we are not saying anything here, we are assuming that these factors are independent orthogonal. So we will see the assumption later on. With this, if I want to write down certain equation, can I not write down regression like equation x1 equal to mu 1 plus lambda 1 1 f1 plus lambda 1 2 f2 like lambda 1 m fm. See here what we are writing, x1 equal to lambda 1 1 f1, lambda 1 2 f2, lambda 1 n fm. What more is there? Delta 1 is there. So plus delta 1. Similarly, you can write x2 equal to mu 2 plus lambda 2 is affected by 1 f1, lambda 2 2 f2 like lambda 2m fm plus delta 2. So in this manner you can write xj equal to mu j plus lambda j1 f1, lambda j2 f2, lambda jm fm plus delta j, and final one is xp equal to mu p plus lambda p1 f1, lambda p2 f2, lambda pm fm plus delta p. Correct. So that means in matrix form you can write x1, x2, xj, xp equal to mu 1, mu 2, mu j, mu p plus your lambda values are there, lambda 1 1, lambda 1 2, lambda 1 m, lambda 2 1, lambda 2 2, lambda 2 m. So, like this lambda j 1, lambda j 2, lambda j m. In the same manner lambda p 1, lambda p 2, lambda p m into your lambda f, f 1, f 2, this will be your, let it be f j, then your what will happen ultimately f 1 to f m. So, I am not giving f j, I let it be given f k and f m. What is happening here then? You have p cross 1 equal to p cross 1 plus this is p cross m into m cross 1. Then one more thing is there, that is delta. So, you will write delta 1, delta 2, delta j and delta p. Okay. So, now I am writing this in matrix notation x equal to mu plus lambda, capital lambda f plus I can write this is delta. You can write like this. So, what will happen? Actually, this one is your x, this one is your mu, this is your lambda, this one is f and this one is delta. So, as a result, your dimension p cross 1, p cross 1, p cross m, m cross 1, p cross 1. This is what is dimension. So, now you can further simplify this x minus mu lambda f plus delta. So, mean subtracted original variables is a function of the factors plus error. This equation, if I say 1, this is the factor model. Okay. This equation is known as factor model. This equation will be further handled through several assumptions. I think all of you know that expected value of x is mu, covariance of x is capital sigma. Now, what will be the our assumption is expected value of f, this one is 0. The reason is you have taken mean subtracted. So, expected value of f is 0. Assumptions, expected value of delta, that is error term, that is 0. Okay. Now, we want to make this type of things, that covariance of f is expected value of f transpose, because expected value of f is 0, this one, this will be I. And your covariance of another one, the delta, that will be psi, which is a diagonal matrix psi will be P cross P, so PP. And covariance of F delta, that is 0. That means F and delta, this covariance is 0. So, these are what are the assumptions under. If these assumptions hold, then this factor model is known as exploratory factor model. Orthogonal, definitely exploratory plus orthogonal. Okay. So, here I think I should say a little bit of as we have started with little bit of the types. We are saying orthogonal because they are independent. F1, F2, Fm, they are independent. There will be oblique factor model when you will say no, they are not independent, there is correlation between them. Getting me? So, this correlation coefficient will be phi 2 1, this will be your phi m2, this will be your phi m1. So, when you allow covariance component between the factors, then your factor model will become oblique factor model. Now, this oblique factor model will be treated separately, and we will discuss orthogonal factor model. Thank you very much.